So previously, we learned about exploring our dataset using different tools like Matplotlib, NumPy, Pandas, making different plots, and getting to know a dataset to its depths. So now let's do something more interesting. So let us say that we have a list of numbers in a dataset, for example, a diabetes dataset. So what we are going to do is we'll use this diabetes dataset, which has a set of 10 features and 42 samples, and also a target variable, which is a numeric value supposed to represent how much the disease has progressed. So what we want to do is let's use only one of these features out of the 10, and let's try to predict the disease progression. So let's just import all the libraries. By now you must know the NumPy, Pandas, Matplotlib as well. And we'll get into more detail about the train test split in a bit. So let's just import these libraries and also run the magic command matplotlib inline so that all the plots that we draw are shown in the notebook itself. So first of all, you could use the load dataset function from the sklearn datasets like such. But I have already downloaded this dataset and saved it in a CSV file. So I'll just read it in a data frame using the read CSV function. So data equals to pd dot read CSV, and we'll just have to give this the path. Now, as we saw in a previous video, we can explore the data using the head command, head method. So we have these 10 features. The S1 to S6 are all some blood sample test results. We have the age, the sex, the BMI, and the blood pressure of the patient. And this is the target variable that we want to predict. So what we'll do is we'll only consider the BMI for now to make things easier. And we'll try to predict the target variable. So what we'll do is first let's separate these out. So let's say x equals to data. So now if you see, we get a pandas series, which has only the values from the BMI column. But to make things easier for computations further, what we'll do is instead of getting a pandas series, we'll get a numpy array. To do that, we can just use a toNumpy function on a pandas series to get a numpy array instead. So now if you see this, we just have a single array of large numbers, right? So first of all, let's try to see the data a little more visually. So that we can get a better idea of how it's spread. So as we learned in one of our previous videos, we can do this using a scatter plot. So we'll not make the graph too fancy right now, but just see how the values are spread. So this is the disease progression over here on the y-axis from 50 to 350, and over here from -10 to minus 0.1 to plus 0.15, we have the BMI of the patient. So now if we see over here, you might think that there is a positive correlation in the BMI and the diabetes, the target variable, right? Generally the higher values of BMI have a higher target value, the higher disease progression. So what we might think of doing is that since we have the values spread somewhat like this in a positive correlation manner, the simplest way you might think of trying to predict any value given the value of the BMI, the simplest way you might think that we might want to predict this value is just draw a simple line that tries to fit this data the best. And then given this values, let's say X over here, we just go to the corresponding point Y on this line and say that that is our prediction. So that is a very simple approach that we could use to try to predict the value of disease progression given the value of BMI, right? So that's great. But how would you do that, right? Because when given a plot like this, how would you go about finding a line that you think fits the best on the data? Let's say you have a line like this, and you also have a line like this. How do we define that which line fits the data better? We need a proper quantitative measure, right? Otherwise, there is no point in saying that this line fits the data better than this line. It's easier to say that this line does not fit the data very well, and rather these two lines fit the data much better. But you could easily say it visually. But for us to make a computer program that is able to compute a line that fits the data good, we have to define some exact measure of how we can say how much the line is fitting the data. So one thing that we can do is, let us say that we have some points along the line data like this, okay, and this is our line. So what we do, we compute this distance over here. uh, let's call this dx for now, for every single point, for this, and then add up all these distances as a measure of error of how much our line is not predicting the result accurately. Since you can say that the distance over here is some sort of a error, right? Because if we plugged in a value of xo at this point, our line would give the answer as this, but the actual point is over here, right? So the quantity that we just are trying to calculate is actually called the sum of residuals. The residuals. Since this uh, since this part, the difference in the actual and the predicted value can be thought of as a residual, and we are just summing all those up. And to make things even more simpler, in the thing that we did now, you might have also seen that there is a issue that the residual which are below the line and the residuals which are above the line might, if they are equal in value or even if they are not, they cancel each other out, right? So let's say this value here is 5 and this is -4, so we'll get a sum of residuals 1, which might be thought of as a good uh, error, right, since it's very low. But actually the line is not performing very well because it cancelled each other out. So what's actually done in practice is that we square those residuals. So what we do, instead of just adding all the differences, we square them first, right? So that is called sum of squared residuals, the sum of squares. You can also denote it as SS. So that gives us a good measure of how uh, good the line is fitting, right? So a line, let's say this one, let's say this is just the mean of the data, right? So it's the mean of y. So this one will obviously have a lot higher sum of squared residuals than this line over here. And that way we'll know that this line over here is fitting the data much more than just taking the mean. And one more thing that is actually done is we also can take the square root of this thing afterwards. Since we squared all the residuals in the first place, taking the square root after summing it up gives us the root mean squared error. The root mean squared error, REL. Okay. but we won't be using that now. We'll just use the mean square error, the mean square error. So the squared, so the sum of square residuals is also called the mean square error, right? So now we know that if we have some data, let's go back to our original data. So now this is the data that we have over here, right? So we want to fix a line in this, which should have the minimum mean squared error. So we know that that line is fitting on this data very well, and we could use that line to make predictions. Okay, so we at least find out what we need to do, but how can we do that? Since visually we could just draw a line like this out of our intuition, but how could we actually get a line that's actually fitting the data really good? So one thing you might be thinking of intuitively is that there might be some formula we might be able to come up with for this line to get a line that fits the data very well, right? But that's very hard to do when you have a lot of points. So first of all, let's go back to our examples. So what we could actually do is, instead of getting the best line directly, we could just start with a normal line like this. And let's say that we want to rotate this line in a way that it reduces the mean squared error. So what we want to do is, so first of all, we want to come up with a line, right? So how do you define a line? So line is just y equals to mx plus c. So this is the equation for a line. We have the slope, which is the m, and the y-intercept. So this over here is the c, and the slope of the line, the dy by dx, is the m. So in machine learning terms, we actually call this m the weights w, and this c we call the bias. So what we want to come up with is an equation for a line, which is y equals to wx, which is weights plus x plus bias, right? So we have to find the values for the weight and the bias, these two variables, such that this line fits the data the best. So one way of doing this is make a line which it does not fit the data but is generally, let's take a mean or just any line, and then slowly modify the weights and biases in such a way that it reduces the mean squared error. So one way to do that is an algorithm called gradient descent, in which what we do is, since we have a cost function, let's actually define it in a more mathematical way. So let's say our function, uh, let's call that j of weights and biases is equal to 1 upon n. Yeah, so uh, one small correction here. So the sum of squared residuals is just the sum of all these squared residuals. But the mean squared error is the mean squared error, since we also divide this by the number of samples. So when you divide the sum of squared residuals by the number of samples, you get the mean squared error. So these aren't exactly the same. So coming back to our cost function. So what we do is, we are taking the sum of I equals to 0 till n, the actual value of I, the y, minus the predicted value of y, right? And this is squared. So this is our cost function. So what we actually want to do is we want to find the values of the W and B such that it minimizes the value of this cost function, right? Okay, so now that we have the cost function, we'll use the gradient descent algorithm to find the optimal values for weights and the bias. So how the gradient descent does this is the gradient is a mathematical quantity. It is the derivative at a point of a function, which also defines the direction of the steepest increase in the value of that function. So since we want to decrease, uh, since this is the cost function and we want to decrease this, right? Because we don't want the cost to be high, we want the cost to be low. So we'll calculate the gradient of this with respect to the weight, with respect to the bias, and then subtract that gradient from our from the current weight and the biases to get to a optimal weight and bias, right? So you'll understand better when we try to do it in code. But just to complete the maths over here, what we'll do is to actually find that we find the partial derivative of this function with respect to W and also with respect to B. So first, before this, we'll actually define the error. So error is just the opposite of the cost, right? So y cap of I minus y of I would be the error. So that is the predicted value minus the actual value. So E would be E of I actually. So this would be X WI plus BI minus Y of I. So let's substitute this term back into the original equation. So what we get is summation of 1 upon n and minus E, because that is the opposite of error, whole square, right? So now let's differentiate this with respect to, so this is our J right now, the J of W comma B. So now what let's do is let's differentiate this with respect to W, the partial derivative. Let's take the partial derivative with respect to the W. So what we'll get is 1 upon n summation of the 2 comes down over here. So this gets us 2e into the partial derivative of e with respect to W. And what is e? E is this term right here, right? So this is just a constant. So this gets cancelled. This is also a constant. So we just get x. So this term over here is just x. Right, so we can take this 2 outside as well. So we get 2 by n summation of e of I into x. So now we know that the error is uh, this, right? Y cap minus y, and we want to multiply it with x. So in matrix notation, we can write this as x, the transpose of the x matrix into y cap minus y, and 1 upon n. 1 upon n. So what we did is we removed the 2 since that is anyways a constant, and in practice we could adjust for that in the learning rate, right? So this is the equation that we got for dw. So this will give us a small step in the direction that we should take to increase the cost function for with respect to w. But since we want to decrease the cost function, we will subtract this, right? So when we are updating our W, what we'll do is we'll use W minus dW into some constant alpha, which in which in the machine learning lingo is called the learning rate. Since we don't want to update this too much, right? Because if we have too big of a steps, so let's just see it with an example. Let us say we have a function over here which goes like this, and this is the point, this is the lowest point, and since we are reducing since we are trying to minimize the value of the function, this is the point we are interested in, and we start with here, let us say, and using gradient descent we are going small, taking small steps and trying to go in this valley and reach this point over here. But what would happen if you take too big of a step? You might directly end up over here. Then again, you take too big of a step, then you might end up over here, then over here, then over. You might just oscillate in this valley and never reach the minimum, right? So that's why it's important to have a small learning rate. Okay, so this is what you get for the weights. Similarly, we'll also do this for the biases. So even for the bias, what we do is we still get 1 upon, 2 upon n, and the summation of e of I, and then the partial derivative of the the error with respect to b this time. So what is x e over here? So now this is just this, right? This is a constant. All these are constants, so we just get 0. So this term cancels out, and we just get e of I. So we get 2 by n, and since this is a summation, we get a summation of the error was just y cap minus y. So this gives us the gradient in the direction of b, correct? So let's just write these two equations somewhere. So we have, in this also we'll just ignore the 2. So what we'll have is 1 upon n, and the summation of y cap minus y equals to db, the small step we want to take in the small change we want to make to the bias to get a lower cost, and say 1 upon n summation of into x transpose, the dot product between the transpose of x into y cap minus y. This gives us the dw. So we have both the equations that we need to try to get the best possible values for the gradient and the bias and the weights. So let's try to build this in code. So what we do is, now since we have x and y and we have the data ready, first of all what we'll need to do is we'll have to reshape this data a little bit and also divide this into training set and the test set, right? Since we also want to evaluate our performance. So for the train and test, it's very easy. What we do is x train, x test, y train, y test equals to, we'll use this train test split function that we got from the sklearn.model selection. This just takes in the x and y values and also the test size. So test size equals to 0.2. So 20% of the data we'll use as the test set. Let's also give it a random state. State of 42 maybe. This is just there for reproducibility, since it uses some other random state every time if you don't give it something yourself. So if you give this, you will be able to replicate this easily on your machine. So this way we'll get the training sets and the test sets. But still there is one problem with this. So what happens is, now if we look at the X train, let's see. This is an array this is just a very long array of integers, right? But the issue over here is, uh, with sklearn or any type of linear regression algorithm or any other model specifically, when you're working with this type of data, how do you know that you're not necessarily only using one feature, right? We might have also chosen, let's say, sex and age as well. In that case, these three integers over here would consist of a single sample. Then this three would be the next sample, right? So we know that we are only using BMI, but since this is just an array of numbers, the computer does not know that, right? So instead, what the what the models from these ready-made libraries or any other machine learning models you will be using in the future most probably expect is a list of lists. So a 2D list as per se. So what that means is, so I'll just show you. So X train equals to, we'll just resize this thing. Reshape, reshape -1, 1. And we'll do the same with the test as well. So now what it did is, if you see, now we got an array where each sample itself is also an array. So now it knows that this whole array is one sample, this whole array is one sample. Even though this only has a single number because we are only using a single feature, it's easier for the computer to distinguish, right? So the reshape function works is this, this is the number of rows that we need. -1 means it figures out the number of rows on its own, and 1 is the number of columns. So that is the number of rows in one of the row, or the number of features in a single list. So if we have, let's say this is, if this is 2, so we cannot, okay, if this is 3, is this not divisible by anything? 353, maybe 7. So we'll just take the first 10 of this, and then we could have it divisible by 2. So now what this did is, what, as you can see, it added two numbers in one list. So this is what it does. Let's get back the arrays. Yeah. So we have the data now. So now let's go ahead and try to make a linear regression model. So we'll define a class, and linear regression, make a init function. So let's take the learning rate. Let's just keep it 0.01 as the default, and also the iteration. So we can also call that epochs. And let's also take in epochs. Epochs means the number of times we are going to iterate our learning mechanism, which is in this case the gradient descent. So for now, let's just keep it as 1000, right? So self dot rate equals learning rate, self dot epochs equals to self dot rates equals to none, or to start with, self dot bfis equals to none for starting. And let's also uh, keep an array of the history of costs that we have in each iteration, just so that we can visualize it later. Cost history, empty array. So now actually let's go ahead and code up the gradient descent function. So let's call that function fit. So it will take in self, x and y, right? So first of all, since we are only using BMI, we are going to have a single feature only. But let's make this implementation a bit more general, and instead of just assuming the shape of the input, we'll take the shape from the shape property of the input data. So number of SAM, alias samples, comma number of features equals to x dot HSE shape, right? Then let's initialize the weights array. So self dot weights equals to numpy dot z eros rows, and the dimensions would be how many number of features there are. So for now, since it's just one feature, it will be a single array with a 0, and self dot b bias equals to 0. So now gradient descent. So for I in range, let's go till the number of epochs, right? Self dot epochs. What we have to do. So first we have to predict y. So that would be the x into self dot weights plus self dot bias. And you can't just multiply them directly since they both are numpy arrays. So we have to use np dot dot. So we take the dot product of the input data with the weights and then add the bias. So we get the predictions. After we have the predictions, what we have to do, we have to calculate the gradients. So over here, we got the formula for the gradients, right? We have 1 upon n into y predicted y minus y, which is this db, the summation of this, and again 1 upon n into x transpose, and again this the predicted y minus y for the gradient of weights. So now let's calculate those. So db equals to 1 divided by n into np dot sum y predicted minus the actual y, and the dw would be again 1 by n into np dot product of x dot t and this thing over here, right? So this is how we got the gradients. Now let's update the weights. So self dot w weights minus self dot learning rate into dw, the same thing for the bias db. And since we also want to store the cost history for each iteration, we'll just calculate that. So cost equals to the mean squared error, right? So it would be 1 by n into np dot sum y minus y predicted whole squared. So this is the mean squared error, and we'll just append it to this. Right, and if let's say after every 100 iterations, let's also just print the cost to the screen so that we can see if we are improving or converging to a solution. So if I mod 100 is 0, actually I plus 1 mod 100 is equal to 0, then print and let's just return self. Right, so we made a linear regression model. We made of we defined the constructor with the learning rate, epochs, weights, etc. And we made the fit function. So fit is actually just the training function. So when we fit this on some data, that means we are training our model on that data. So what we are actually doing is we are just calculating the weights and biases such that the line that we have fits the data the best. So now after we have the line, we also want to predict, right? So def PREDIS predict something new. So this function then is take an x, just return the predicted value, which is just wx plus b. So then dot weights into x plus then dot bias. Right, so dot product between these two. So this predicts the thing. So now that we have the model, we'll also want to check how good is it performing. So what we actually want to check is that the line that we are fitting on the data and then using to make predictions, how good the predictions are, right? Otherwise, how would you know that uh, how good of a model have we made? So for that, there is a metric called R squared. So R squared. So how R squared is actually defined is the variance the variance near the mean minus the variance near the fit line. So line that we fit divided by the variance near the mean. So what this actually means is that let's say we have some data. So what we do is we have, let's say this is the line that is just the mean of y, right? So this is the y mean. And this is the line that our model made after going through all the gradient descent and all. So what we do is the variance over here just means that the mean squared error. So we calculate the mean squared error over here with respect to this line, the mean line. And we also calculate the variance with respect to the line that we predicted. For some of them it's more, for some of them it's less. But overall, for the line that we have fit on the data, the variance would be much lesser. So what we are actually trying to measure over here is that how much of the variance in the data can be explained by the feature that we are using for the linear regression. So let us say that the R square value for this over here we got would be, let's say this can be 0.5 and this is 0.2. So this is also 0.5. So we get 0.3 divided by 0.5, so which is 0.6. So what this means is that 60% of the variance in the data can be explained using that feature. So if this was BMI, for example, that means using the BMI, we could explain the 60% of variance that we see in the diabetes progression. So the higher value for R square are better. So more the value for R square, the more the value, the better your model is performing. So that's that's a good measure for checking how good your model is performing. Always make sure that that is not the only measure you can rely on, since let's say you only had 2 points. So you could always fit a line that goes through all these points perfectly, right? Because for any 2 points, there is a line that goes through them. So that means you'll always get the R square of 100%. But that doesn't mean that your model is very, very nice, right? Because they are just 2 points and it might not fit the test data so much. Let's say this is all the test data. So on the training data, your model has fitted 100%, but on the test data, it will give you a 0% performance. So that's why the one more thing that is done when calculating the performance for these models is the p value for the corresponding R square value. But we'll dive deep into the p value in another video. For now, let's just calculate the R square for testing the performance of our models. So let's call this score. So we'll take again x and y. So what we'll do is y predicted would be, now that we have a function predict, we can just call self dot predict for x, and then let's say u would be y minus y predicted whole squared dot sum, and v would be the same thing, but y it would use y dot mean instead, and then the score would be, we want to return the r, that r squared score, right? So will be 1 minus u upon v. So this is the R square score. So now that we have all the functions in place, let's actually train this model and see how does it perform. So this was the data that originally was there. So now let's fit our model onto this data. So MODEL model equals to a linear regression model. Let's give this a learning rate of 0.01 and use 2000 iterations. Let's first only use 1000. Let's see what happens. Then MODEL model dot fit on x and y, right? So let's see. Uh, there is cell, then x, then y. What is the issue? Okay, sorry. We have to use the x train, right? And y train. X train, Y train. Yeah, so for dot products, you don't multiply, just give a comma over it. Why is n not defined? N is the number of samples, right? Let's just call this n itself. Yeah, so see, the cost is decreasing, and we can see that our model is getting, it's fitting pretty well. Let's also score the model, model.sc or score on the test data instead of the train data, and let's see what happens. Okay, over here as well, it's the same issue. Yeah, so now we got the score. Let's also do this for training as well. So xtrain train and y train, and then so let's also print these values in a more human readable way, so that this is the train score and this is the test score, right? From this and this. Yeah, so as we can see, the models that we trained learned the bias 153, learned the weight 22. This was the R square on the training data, and this was on the test data. So not very good, you might say, but it's trying its best. But just seeing this number doesn't make us properly understand how the line has fit, right? So what we could do is, let's just also plot the line on this chart as well. So let's see what the fit is. So let's move this down over here. Let's make the plot a little bigger. lt.fiq figure fig siz fig size equals to 10,6. Let's plt dot plot x. Let's actually just plot the test lines, right? So it's not too cluttered as well. Test, est test, and model model dot preds predict for s comma test, and color equals to, let's make it red. Okay, so as we can see, the line is not really fitting that well. So even though our model is learning and the cost is getting less, the line itself does not fit too well. So what can we do to improve the fit? So first thing that we might want to try is, let's try to increase the learning rate, because maybe it's not getting enough time to learn the actual features. And we'll also uh, increase the number of iterations, let's say 2500. Now we'll do this again. So now it has learned a different weight, a different bias, and now is, if we can see, the R square scores are also much, much better. So now if we see this, we have a much better plot, right? So one more thing that we can do to improve this is, yeah, so one more thing that we can do to make the fit even better is actually scale the features. So what we'll do is, from sklearn dot pre-processing, yes, yes, I am pre-processing, I am pure import standard scaler. So what scaling does is that since we have the features which are very small, right, which are from ranging from minus 0.1 to 0.15 as we saw on the plot earlier. So instead, it will scale these values to be much closer to 0 and 1. And since when we scale the values, the gradient descent is able to learn much faster. So what we do is we have X, TRA and train, SE, and it is scaled could be standard scalar fit TRA and X. Fit transform X train and X yes we test SE and it is scaled equals to this time we can just use transforms since we are dealing with the same kind of data. So fitting on X train is enough to transform the X test as well, right? Okay, we also have to make a scalar. CNA scalar equals to standard scalar. And then we can use this. Yeah, and now let's use these values actually. So train on this. So now as you can see, the cost has decreased a lot. And now we scaled. We can see that we are getting much better training and test results data. So now if we plot this as well, so let's also use see and it is scaled ones over here. Actually, we don't have to use the scaled ones here, but just the scaled ones in the predictions. So now as we can see, the data is fitting much better because we scaled the features. So this is also one way you could improve the performance of your gradient descent models. Now that we have seen how to implement a linear regression model from scratch, let's also implement the same model using sklearn. Since in practice, most likely you will be using those libraries and not implementing it from scratch. But it's good to know how to do it to understand the concepts. So let's implement this same model and train it on the same data, but this time let's use scikit-learn. So again, we'll just import numpy, pandas, matplotlib like always. We'll also import this, but since we have the dataset already on the computer, we don't need this. The train test split, linear regression. This time we are just importing the linear regression model directly from sklearn and the R2 score as well, which we calculated from scratch earlier. So let's run these two. Let's get the data. So we'll be using the same code to get our train test split. And this time what we'll do is we'll not use the standard scalar, since even without that we'll get good results, and there's a reason for that which we'll talk about soon, and we don't have to define this model ourselves. So let's get the data. We can directly just use model equals to linear regression. So now we got a linear regression model. So let's use this to make some predictions. Okay, yeah, so we will have to pass in the X values to make the predictions. These were the labels. Yeah. So now that we have gotten the predictions, let's also get the scores, the R2 scores. So train score equals to R2 score, which would be the Y train and the Y train predictions, and test score, which would be the Y test and the Y test predictions. And let's display this like we did before. So this time to get this, we actually use the COEF, the coefficient, to get the weight, and for the bias we use the intercept. The others are the same. Okay, it's COEF underscore. So now as we can see, it has also learned some weight and biases, and it is almost performing as good as our, it's actually performing better than the model that we trained using the gradient descent. Over here we got 0.36, 0.233, over here 0.36, 0.233, 5734. So it's performing almost the same, actually exactly the same, but it has still learned different weights and different biases. So why is that the case? First, actually, let's also plot the line so we can see that. So instead of, so as we can see, the line also looks very similar. And if we see, even though with the different weights and biases, we are getting a very similar line and also a very similar score. So even though our model was able to perform as good as this library model, why are still the weights and the biases that we learned different? So what actually happens under the hood is the linear regression model from sklearn doesn't use gradient descent by default. It actually uses the normal equation. So that's an analytical closed form solution, which you can use to directly get the optimal values for the weights and the bias. So even that is also implementable in our from scratch approach. But we'll learn about that in the next video.